All right, let's jump right in. Today, we're tackling two of the biggest, most important ideas in all of statistics. We're going to decode a pattern you've definitely seen everywhere, and then uncover this kind of statistical superpower that lets us make some really powerful predictions from just everyday data. So let's get into it.
So let's start with a question. You've seen this shape before, right? Of course you have. The classic bell curve. It just pops up everywhere, in test scores, people's heights, even tiny measurement areas in a lab. It's kind of weird when you think about it. Why? Why does so much of the messy, random data in the world seem to line up and follow this one, simple, elegant shape?
Well, that pattern has a name, and honestly, it is the absolute cornerstone of modern statistics. It's called the normal distribution. It really is the most common pattern you'll find out in the wild, and getting a handle on it is the key to unlocking a huge chunk of any data scientist's toolkit.
And you know, the wild thing is how this universal pattern boils down to something so simple. The normal distribution is what we call a continuous probability distribution, meaning it covers a whole smooth range of outcomes. And that iconic bell shape? It's completely defined by just two numbers, its center, which we call the mean, or mu, and its spread, the standard deviation, or sigma.
The best way to think about these two things, the mean and the standard deviation, is like two control knobs. The mean, mu, sets the location. It's the middle point, the very top of the bell. You change the mean and the whole curve just slides left or right on the number line. Then you have the standard deviation, sigma. That knob controls the spread. A really small sigma gives you a tall, skinny curve. All the data is bunched up tight around the center. A big sigma gives you a short, wide curve, where all the data is way more spread out.
Okay, so we can describe the shape. That's cool. But so what? What does this curve actually tell us? How do we go from looking at this shape to actually saying something meaningful about the probability of our data?
This is where our first tool comes in, the probability density function, or PDF for short. The easiest way to think about it is that it literally just draws the bell curve for us. The height of the curve at any given spot tells you how likely it is to find data right there. So the peak, the highest point, is where the data loves to hang out. The tails way out on the sides, not so much.
But what if you want to know something a little different? Like, what's the chance of scoring 75 or less on a test? For that, you need the cumulative distribution function, or CDF. It's all about adding up the probability. It takes all the area under that curve, starting from the very far left, and adds it all up until it gets to the point you care about. It accumulates the probability for you.
Okay, this all seems incredibly useful, but hang on a second. This whole thing works perfectly if our data already follows this beautiful, symmetric bell curve. But real life isn't like that, right? Real-world data is often messy, it's skewed, it's lumpy, it's just plain weird. So does that mean the normal distribution is totally useless when we're dealing with the real world?
And the answer to that is a huge, emphatic no. And this is where we get to probably the single most important idea in all of statistics. I'm not kidding. I like to call it the data scientist's superpower, the central limit theorem. This is the magic bridge that connects that perfect world of theory to the messy world we actually live in.
So here's the big idea behind the central limit theorem, or the CLT. It basically says that if you take the average of a bunch of random stuff, the distribution of those averages will start looking like a bell curve. And here's the kicker. This is true even if the original stuff you were measuring wasn't bell-shaped at all. This one insight is the engine behind everything from A/B testing to political polling.
So how does this actually happen? It's like a recipe. First, you start with any population. I don't care what it looks like. It can be totally weird. Second, you start pulling out lots and lots of random samples from it. Third, for each one of those little samples, you calculate its average. Now, for the amazing part, you take all of those sample averages you just calculated and you plot them on a histogram. The shape that starts to form, you guessed it, a beautiful, predictable bell curve.
Okay, that sounds magical. Maybe a little too good to be true, but I'm still trying to see how this helps me solve a real problem. Can we see it in action?
You bet. Let's take a classic example. Flipping a fair coin 100 times and counting up the heads. The result of that follows something called a binomial distribution. You can get exactly 48 heads or 49 or 50, but you can never get 49.5 heads, right? It's a series of separate, distinct outcomes. It's all these little bars, a blocky staircase, not a smooth slide. Now, here's the problem. What if I asked you what's the probability of getting more than 60 heads? Well, the old-fashioned way,
You'd have to figure out the exact probability of getting 61 heads, plus the probability of getting 62, plus 63, all the way up to 100, and then you'd have to add all those tiny numbers together. It's doable, but wow, is it tedious?
But here's where the magic comes in. Because flipping a coin 100 times is really just 100 little independent trials, the central limit theorem kicks in. It tells us we can use a smooth, easy-to-use normal distribution as a really, really good approximation. This turns that horrible multi-step calculation into something way, way simpler.
And check out how easy it is to figure out which normal curve to use. For this kind of distribution, the mean is just n times p, the number of trials times the probability. So 100 flips times a 0.5 probability, that's 50. Easy, that's our mean. The standard deviation formula is a little hairier, but it's just plugging in numbers, and it comes out to exactly 5. So now we can answer our tough question using a simple normal distribution with a center of 50 and a spread of 5. So much easier.
So, let's take a breath and look back at where we've come. We started with a really simple question about a shape we see all the time, the bell curve. That led us to the normal distribution, and that, in turn, led us to the central limit theorem, which is the key that lets us use that simple shape almost anywhere we want. So, let's really nail down what we learned.
So let's boil it all down. First, the normal distribution is this fundamental pattern that just shows up everywhere. Second, the central limit theorem is like a magic key that lets us use the normal distribution to understand the average of almost anything, even if the original data is a total mess. This is what makes it possible to make powerful predictions from just a small sample of data. It's the engine running under the hood for things like A/B testing and confidence intervals. And as we saw, it can turn a horribly complex calculation into something pretty simple.
So I'll leave you with a question to chew on. Now that you know how to spot this fundamental pattern, and more importantly, how to use it even when it's not obvious on the surface, think about your own work, your own data. What new insights could you find? What powerful predictions are just waiting to be made? What hidden patterns could these tools reveal for you?
And that is a wrap for this deep dive. If you got something out of this, do me a favor and share it with a friend who you think would dig it too. And of course, hit that subscribe button so you don't miss the next one. Thanks for hanging out.